Hello, everyone, and welcome to Lecture 5 of Computer Architecture. Today, we're going to talk about logic design. We started talking about logic design last time. We looked at some of the fundamentals, and we're going to continue looking at some of the fundamentals of logic design today. So last time, we started talking about logic design. This was the beginning of part 1 of the course, which covers this bottom layer over here. Which is going to cover logic design and computer arithmetic, which correspond to Appendix B and Chapter 3 in the textbook. We said last time that this layer of logic design is involved with taking logic gates and being able to build circuits that do more complex things like adding, multiplying, selecting, or storing memory. And we said that there are two general categories of logic blocks. There's combinational logic, where the output of the block depends on only the input to the block. And there's sequential logic, where the output depends on both the input as well as values stored in the block. We started talking about combinational logic, and we said that we'll be talking about combinational logic for a few lectures, and then we'll continue to talk about sequential logic. We looked at various ways of specifying the behavior of logic blocks. One way was a truth table. So here, if our example was a car warning system, which would beep if some combination of events took place. For example, if you opened the door and your key was still in the ignition, or if you removed the key from the ignition and the light was on. So here we saw how we can specify the behavior of this logic block using a truth table, and we also saw that you can specify the behavior of a logic block using logic equations. We looked at how we can extract a logic equation from a truth table. This was one way to do it. We'll look at other ways to do it today. We also said that logic gates are used to build circuits. And just like any logic equation, any logic functionality can be specified using just and, or, and not operations, any logic circuit can be built using just and, or, and not gates. And for example, if we have this equation here, D equals not A and B or not C, we can build a circuit that computes this operation by combining an AND gate, some NOT gates, and an OR gate to fulfill what the circuit does. And we said that, because these inverters are so common and they're a little bit tedious to draw, we can, for shorthand, just put these bubbles at the input of gates, which indicate that there's an inverter, that the signal is passing through an inverter before it goes through the gate. We looked at uniqueness of implementation, and we said just like there's a unique truth table specification for a logic block, but there is not a unique equation. Some equations are more complex than others, and therefore the circuits that correspond to these equations are also not unique. So we can have different circuits for implementing a logic block, and if you'll notice. This circuit over here, how expensive it is to implement a circuit corresponds to, loosely speaking, the number of gate inputs. So the circuit on the left here requires 19 total gate inputs, and then the circuit on the right only needs 7 total gate inputs. And that's why the one on the right is more efficient to implement in hardware. And what we wanted is we wanted a way to systematically be able to find what is the cheapest representation of a logic block, to be able to find the simplest equation and therefore the simplest circuit. And to do that, we introduced a technique called Karnaugh maps. So we saw how with Karnaugh maps, we can take the truth table, lay it out on a two-dimensional grid where A is represented in this dimension and B is represented in this dimension. And then we looked for the largest rectangles that are powers of 2 to cover all the ones. And from these rectangles, we were able to derive an equation. And we did this for a two-variable input logic block. And we also looked at logic blocks with 3 variable inputs and saw how to do Karnaugh maps for that. And an important important aspect of three variable Karnaugh maps was that since we only have two dimensions, we had to place A and B together on the same dimension. And to do that, we had to use gray code so that we only have one bit changing between each column. And this was essential for us for the Karnaugh map technique to work. And so here, that's why we had 0, 0, 0, 1, and then 1, 1, 1, 0, as opposed to 1, 0, and 1, 1. Because if you put 1, 0 over here, then we would have two bits changing at a time between this column and this column. And if we did that, then the Karnaugh map technique would not work. Okay? And then we did another example of a three variable Karnaugh map. And this was the car warning system example that we had been talking about throughout the lecture. And this was the equation that we arrived at, which was similar to the same as the previous equation that we had seen was a simple, a cheap representation of the logic block. Okay, so with that, that was a review of last time's lecture. Today we're going to continue talking about logic design. Before I start, does anybody have any questions about last time's lecture before we jump into today's lecture? Okay, if there are no questions, then let's get started. So last time we saw 2 and 3 variable Karnaugh maps. Today we're going to look at 4 variable Karnaugh maps. So the 4 variable Karnaugh map, again, since we only have 2 dimensions, what we're going to do is we're going to put A and B. So if we have 4 inputs, A, B, C, and D, we'll put A and B on one dimension, and we'll put C and D on one dimension. And just like with 3 variable Karnaugh maps, we used gray code. We're also going to use gray code. So here, A and B are using gray code. And also, on this dimension, C and D are using gray code. Okay? Now, if you notice in this Karnaugh map, these two columns together, if they are all 1, these correspond to an A is 1. Okay, so here you'll notice that A, B is 1, 1, and 1, 0. So in both cases for these columns, A is 1. So these correspond to an A is 1. And then by exclusion, these two columns over here correspond to an A is 0. In other words, they correspond to not A. The two columns in the middle, these correspond to B. So you'll notice that because we have 0, 1, and 1, 1 over here, because we used gray code, and for both of these columns, B is 1, and therefore these two columns together represent when B is 1. Similarly, these two rows at the bottom represent when C is 1, because here we have 1, we have 1, 1, and 1, 0, so C is 1 in both these cases. And then these two rows in the middle represent when D is 1. Okay, let's look at an example of how we can use a 4 variable Karnaugh map to simplify a 4 input equation. So let's say we had this truth table over here. The first thing we want to do is we want to take this. We want to extract the simplest equation that represents the specification in this truth table. So what we're going to do is we're going to take this truth table and we're going to lay it out on the Karnaugh map. So here we're going to have a 4 variable Karnaugh map. We have A and B up here, C and D down here. And the way we're going to do it is as follows. So look, if here we have 0. Here, when A, B, C, D are 0, 0, 0, 0, the output is 0. So here we have 0, 0, 0, 0, and then the corresponding output is going to be 0. And we do that for all of these cells. And kind of a quick way to do it is we have here 0, 1, 1, 1. So we put a 0 here, then we put a 1 over here, and then we skip, and this is important here, we skip this third row and we go down here, we put the third one over here, and then we go back to the third row and we put the fourth one over here. And that's because here we're using gray code. And here we're not using gray code. Here we did 0, 0, 0, and then 0, 1, 1, 0, and 1, 1 for C and D. Okay, so the first 4, 0, 1, 1, 1 are going to go here, 0, 1, skip the row 1, and then come back and put a 1. The next 4 bits are 0, 1, 0, 1. So we're going to put those in the second column over here. We're going to put 0, 1. We're going to skip the third row. We're going to put a 0 here. Then we're going to come back and put the 1 over here. Then the third 4 bits are 1, 1, 1, 1. Now this is also important. Again, we're using gray code here, so we're going to skip the third column. We're going to go to the fourth column, and we're going to put the 4 ones over here. So we're going to do 1, 1, skip the third row, put a 1 over here, then come back and put a 1. And then finally, we have 0, 1, 0, 1. We're going to put a 0 and a 1 in the. We're going to come back to the third column, put a 0 and a 1, and then we're going to skip the third row, put a 0 down here, and then come back and put a 1 over here. Okay, so by doing this, what we've done is we've laid out this truth table on this Karnaugh map. Now that we have done this, the next step is to find the largest rectangles that cover all the ones. So one obvious one is this rectangle in the middle. Here we see that we have these 2 rows are full of ones. Oh wait, before I say that, it helps to draw these A, B, C, and D, these ranges, because they help you kind of find out what is the equation that corresponds to a rectangle. Okay, so the largest, first, the kind of the most obvious largest rectangle here is this one over here. We kind of cover most of our ones using this rectangle. We have these all these 8 ones are all covered by one rectangle. Next, what we can do is we have 1, 2, and 3. These 3 remaining ones. Well, these 2 ones can be covered together in one rectangle. We can put a rectangle that covers this entire column. And this covers these 2 ones. And then what we're left with is we're left with this one over here. Now, again, we want the largest rectangle to cover this one. So we don't want to just put a square on top of this one. We want to get the largest rectangle so that we have the least number of inputs. And it turns out that the largest rectangle to cover this one is these 2 ones. And again, remember, we can wrap around, so we can go in this direction. So we have 2 ones over here. So the largest rectangle is actually this orange rectangle that covers these 2 ones along with these 2 ones over here. Okay, so now we've covered all our ones. The next step is for us to extract an equation that has a term for each of these rectangles. So let's look at the blue rectangle first. What does the blue rectangle represent? What term does the blue rectangle represent? D, exactly. So here, this range D refers to this entire blue rectangle. Okay. Now let's look at this green rectangle over here that covers this entire column. What does this green rectangle represent? Right, exactly. So it represents A and not B. Exactly. It represents A and not B, because here, if you first, one way to do it is to look over here. We have 1, 0 for AB, so it's A and not B. Another way to do it is to look at the intersections. So here we see that A refers to this entire 2 columns, but we only want one of these columns. So to get the second column, we want to do A intersected with not B. So not B refers to this column on the left and this column on the right. So the intersection of A and not B is just this column here on the right. Okay. And then finally, we're left with we have this this orange square that's wrapping around. What is the equation for the orange square? Right, exactly. So we have C, because C covers this entire 2 columns. But then we want to exclude this part in the middle. We want to only include these parts at the end. So it's going to be C and not B, because these 2 columns over here refer to not B. Exactly. So we're going to have D or A and not B, or C and not B. Okay. So by doing this, we've found a simple equation, the simplest equation that represents this truth table over here, that implements the specification of the truth table over here. Okay, anybody have any questions so far? Okay, if there are no questions, then let's move on. So one important aspect of logic design, we would like to, we always want to find the simplest equation to represent a specification. So it turns out that there are some logic blocks where for certain input combinations, we don't care what the output is because these input combinations could never occur together, for example, right? So you have a logic block, it does something. Yes, maybe this logic block has 4 inputs, and these 4 inputs have 16 possible combinations, but we know because of the specific context of the logic block that some of these input combinations are impossible to occur. So in this case, we don't care about what the output is for these input combinations because the input combinations will not occur. And because we don't care, we can take advantage of that to treat them as either a 0 or a 1, depending on what gives us a simpler equation. So in this case, the output in the Karnaugh map is going to be labeled as a D for don't care, and we can treat it as a 0 or 1 during simplification, whichever is more convenient, whichever gives us a better result. So let's look at an example of this. I come back over here. We have this truth table over. Oops. We have this truth table over here, and this truth table has these ones and zeros, but it also has these empty cells because we have certain input combinations that we know will never occur. Okay, if we look at the corresponding Karnaugh map, in this Karnaugh map, what we do is we lay these out. We lay out the 1, 1, and then here we don't care, and then we have a 1. So we're going to have 1, 1, and then we're going to have a don't care over here, D for don't care, and then we have a 1. And then in the next 4, we have D, don't care, 0, 0, 1. So we're going to have D, 0, and then we have 0 down here, and then we have a 1. And then next we have 0D, 0, 1. So we're going to have 0D, 0, 1. And then finally, we're going to have D1, 0, D. So we're going to, and over here, we're going to put D1 and then 0 and then D. Okay. And then after that, what we will do is we will simplify the equation. We use the Karnaugh map to get the simplest equation. So we're going to put these rectangles over this Karnaugh map, and this gives us the simple equation over here. But an important observation is that when we put these rectangles, you'll notice that this green rectangle covers this D over here. So it treats the D as a 1. Okay, if we did not treat the D as a 1, if we treated the D as a 0, we would not have been able to cover these 4 1s because we need a rectangle that's a power of 2. So we'd have to cover these 2 1s on their own, and then maybe this one will be included in another rectangle. But because we treated this D as a 1, we were able to have one big rectangle to cover all these 1s over here. Same thing with this D over here. It allowed us to be able to cover these 4 1s all together, and these 2 Ds allowed us to be able to cover these 2 1s together in one rectangle. So the Ds allowed us to be able to find bigger rectangles because we were able to treat them as a 0, as a 1. On the other hand, these 2 Ds up here, we don't need to cover them, right? So we can treat them as a 0. If we covered them, it's useless because these correspond to inputs that never occur. So by treating some Ds as 1s and some Ds as 0s, we were able to get kind of the simplest equation possible for this Karnaugh map. Are these don't cares clear? Is the use of these clear?
Sir,
Yes.
how do we know they'll never occur?
I mean, this depends on the This depends on the problem that you're solving, right? So here, I just gave you a truth table where we assume that we don't care about a certain set of inputs, okay? But you know, whether where I got this truth table from, that just depends on the specific problem that you're solving to, or specific case that you're implementing the circuit for. Okay, so I'll give you an example. Maybe you have a circuit that's managing a water tank. Okay, and the water tank has a sensor that's on the high and sensor on low. So a sensor tells you when the water has reached the bottom, and a sensor that tells you when the water has reached the top. So it's possible for both sensors to be on. You know, the water is on, the tank is full, so both the bottom sensor and the top sensor are on. It's possible for them to both become off because if the water is very low, both the high sensor and the low sensor will be off. But it's impossible for example, the high sensor to be 1 and the low sensor to be 0, right? It's impossible for there to be water at the top of the tank but not be water at the bottom of the tank. So if you're designing a circuit that kind of handles a water tank like this, you know from the way that water inside of a tank behaves that the input combination of the high sensor being on but the low sensor being off can never occur. Okay, and you can design the circuit accordingly.
Oh, okay, thank you.
Yep, you're welcome. Any other questions? Okay, if there are no questions, let's continue. Okay, now what I want to do is I want to talk a little bit more formally about canonical forms of logic equations. So far, the logic equations that we've been extracting from the truth table and extracting from the Karnaugh map have been in a particular canonical form, and this form is called the sum of products. Okay, you'll notice that all the equations that we've been writing, they've been sum of products. In other words, they've been terms that are ORed together, and each term consists of different inputs that are ANDed together. Okay? And in fact, any logic equation that we would like to express can be expressed in this form. Any logic equation can be expressed as a sum of products, but this is not the only way of expressing logic equations. Another commonly used canonical form is product of sums. Okay, so product of sums refers to when the equation is expressed as a product, so many terms ANDed together, and each of these terms consists of a sum or consists of a bunch of inputs that are ORed together. And just like any logic function can be expressed as a sum of products, it is also the case that any logic function can be expressed as a product of sums. And we've been using sum of products because it's kind of more intuitive for people to reason about. But I'm going to introduce product of sums now, and it turns out to be the case that sometimes product of sums might be more efficient, and sometimes sum of products might be a more efficient way to implement a logic block. So let's take a look at product of sums. So before we had this table over here, and what we did is we extracted a sum of products representation of this table by taking every output where we have a 1 and putting the corresponding term for this output. Okay. So here, for example, we had a 1 for this row. Here we had 0, D was 0, K is 0, and L is 1. So we put not D, not K, and L to represent this output over here. Okay, so there's another way that we could have done this. Another way we could have done it is we could have inverted the truth table. Okay, so here we would have DKL, but here we would have not B. There's supposed to be a bar over the B over here, but it's not showing because of the glitch in the slides or in the animation. It's shown in the slides. So here we're supposed to have, this is not B. It's not. So here we have B, here we have not B. So you'll notice that what we've done is we flipped all the ones and the zeros. So now we have ones in the rows where we had zeros over here. And now we can do is we can use the same approach to extract a sum of products for not B. Okay, so here not B is going to be equal to, well, we have a 1 in this row, so we're going to have D, K, and L are all zeros. So we're going to have a term for not D, not K, and not L, right? And then over here, not B is going to be 1 when D is 0, K is 1, and L is 0. So we're going to have not D, K, and not L. And similarly for the others. So here we have 0, 1, 1. So we're going to have not D, K, and L. And here we have 1, 0, 0. So we're going to have D, not K, and not L. Okay. Now what we do is, this is the equation for not B. What we ultimately care about is the equation for B. So what we can do is we can invert B over here, and we can invert both sides. So we invert B over here, and then we invert this entire equation over here. Okay, and how do we invert this entire equation? What law do we apply to invert what law can we apply to invert something like this? Who remembers? De Morgan, exactly. So when we apply De Morgan's law, what happens is all our ands become ors, all our ors become ands, and all our inversions become normal non-inversions, and all our non-inverted variables become inverted. So that looks like this. So here we had not D and not K and not L. This becomes D or K or L. And notice that, and then this or over here is going to become an and. Here we have not D, K, not L. This is going to become D or not K or L. And then this or is going to become an and then we have not D, K, L. This is going to become D or not K or not L. So again, all the variables are kind of inverted. All the ands become ors, and then all the ors become ands, and we get this equation over here. Okay, so these two are perfectly valid ways of representing B. The one on the left is a sum of products, and the one on the right is a product of sums. Okay. Now the sum of products is usually easier to reason about, but the product of sums is equally is an equally good representation. And again, these are not the only two canonical forms. There are all kinds of ways to represent an equation, but these are kind of the two most common ones that are that are used. Right, I'm going to talk about Karnaugh maps later, but somebody correctly observed that in Karnaugh maps we use zeros instead of ones. That is correct. Okay, let's now take a look at sum of products and product of sums a little bit more formally. So the sum of products, these products over here, which include all the variables. Again, this is a non-simplified equation. What we have is we have a term for every row in the truth table. These terms that have all three variables and correspond to a single row in the truth table, these terms are called min terms. And on the other hand, for product of sums, these terms, which correspond to, again, different rows in the truth table, so these terms correspond to the ones in this truth table on the right, which correspond to the zeros in this truth table on the left. Okay, so these terms are referred to max terms. And in fact, if we have a truth table like this, 0, 0, 0, 0, 0, 1, etc., every row in this truth table has a corresponding min term and a corresponding max term. The min term refers to when kind of the output it refers to the min term refers to when this combination gives 1, and the max term refers to when this combination gives 0. Okay, so you'll notice that this combination gives 1 when we have not A and not B and not C. In all other cases, this combination will give 0, and that's the min term. And then this combination will give 0 whenever we have A or B or C, and that's the max term. In all other cases, this combination will give 1 for A or B or C. Sorry, or all other combinations will give 1 for A or B or C. And all other max terms will give 1 for 0, 0, 0. Okay, oops. So a sum of products is essentially, if you want to extract a sum of products, a non-simplified sum of products from a truth table, it's just going to be the sum of the min terms where all the rows are 1. And a product of sums is just going to be the product of the max terms where all the rows are 0. Or all the rows that have output 0. Okay, so this is how we can extract a non-simplified product of sums from the truth table. Now let's look at Karnaugh maps. So let's see how we can use a Karnaugh map in order for us to extract a product of sums. So what we can do, this is our previous example for the car warning system, where we extracted this simplified equation. What we can do to extract a product of sums is we can invert the truth table. Okay, so here all the zeros become ones, and all the ones become zeros. Okay, so we invert the truth table. Now we invert the Karnaugh map. Now this Karnaugh map on the right represents not B, right? The one on the left represented B. The one on the right represents not B. And now what we do is we find the largest rectangles that cover the ones. So here we find this rectangle over here to cover these two ones, and this rectangle over here covers these two ones. And then what we do is we extract the equation for not B. So what does this blue rectangle represent? Right, it's not D and K. And then the green one? The green one is not L and not K. So here, not B is going to be equal to not K and not L, or not D and K. And then we apply De Morgan's law. So B is going to be equal to K or L and D or not K. Okay? So this is how we can use a Karnaugh map to extract the simplified, a simple equation for a simple product of sums for B. Okay? Is this clear to everyone? Any questions? Now, of course, there's quicker ways to do this. For example, rather than having to redraw the Karnaugh map and then drew the rectangles on the redrawn Karnaugh map, you can simply have drawn the rectangles on the zeros in this Karnaugh map. So that's kind of one quick way to do it. But I did it in steps like this, just so that you guys can kind of follow along more intuitively what is going on. Okay. Someone's asking, we always have to do the sum first to get the product. Actually, you don't. You don't have to do it in steps. I did it in 3 steps, just in order for it to make sense to you intuitively. But it's some people, they will just draw rectangles over these zeros, and then from the rectangles be able to directly infer this term over here, rather than having to do the sum of products first and the product of sums. Okay, so you can go directly from this Karnaugh map here to the equation over here, but I did it in steps just because it's easier to understand and it's easier to explain, and also you're less likely to make mistakes if you do it in steps. Okay, any other questions? All right, let's move on then. Let's do another example. This was our original example, which had the don't cares in it. So let's do another example with a 4-variable Karnaugh map. So first thing we're going to do is we're going to invert the Karnaugh map. So the ones are going to become zeros. The zeros are going to become ones. What about the D's? What happens to the D's when we invert the Karnaugh map? Right, exactly. The D's are just going to stay D's, exactly, because if we don't care if they're a 0 or a 1. So if we don't care if something's a 0 or a 1, we don't care if its inverse is a 0 or a 1, exactly. So here all the ones become zeros, all the zeros become ones, and all the D's stay as D's. The D's stay the same. And now that we have this Karnaugh map, what we're going to do is we are going to now draw circles over the ones in this Karnaugh map. Or we draw rectangles over the ones in this Karnaugh map. So the first rectangle is over here. We can find that this entire row can be covered with a rectangle. And there's an important observation here, which is we can use the same D for both the sum of products and the product of sums. So here, this D was useful when we were circling the one, when we're kind of covering the ones, but it's also here when we're covering the ones in the product of sums. In other words, covering the zeros. Okay, so for this representation over here, we treated the D as a 1, but for the product of sums simplification, we're treating the D as a 0, because here it's a 1, which means in the original, we treat it as a 0 in the original input, as an original input. Sorry, as an original output. We can also have this rectangle over here to cover this one over here, and we're left with this one over here, so we have this orange rectangle to cover this one over here. Okay, now that we've so right, D is 1 in the inverted Karnaugh map, which means it's a 0 in the original Karnaugh map. Okay. So basically, if we were doing this quickly by just covering the zeros in this original Karnaugh map, then we would have treated this D as a 0 in order to cover all these 4 zeros. Okay. All right. So now let's extract the equation. What does this this blue rectangle represent?
Sir, I have question here.
Yes, go ahead.
We care for the ones to cover ones in both cases, right?
Yes, we care to cover the ones in both cases, exactly.
In both
But
cases.
logically,
So
when we're
here
covering
in both cases, it's better to be 1 in both cases.
yes,
right?
we're covering ones in both cases. But what I'm saying is that logically, when you cover ones in the inverted Karnaugh map, it's like you're covering zeros in the original Karnaugh map.
Oh, okay.
Okay, that's what I'm saying. So here we're treating the D as a 1. So it's as if we treated it as a 0 in the original Karnaugh map. But when we got the sum of products, we treated this D as a 1. But when we're getting the product of sums, we're treating this D as a 0. Okay. Okay, so what does this blue rectangle represent? Right, it's C and not D, exactly. What about the orange one? Right, it's A and not D. What about the green one? The green one is it's not A, right? And then B, so not A and B gives me this entire column. And then I do not C, which leaves me with these two over here. Okay, so we have C and not D, not A, B and not C, and then A and not D. Okay, so this is not E. And then what does E become? We applied De Morgan's law, right? So we applied De Morgan's law. E here we replace all the ands with ors, we replace all the ors with ands, and then we invert all the variables. So here C and not D becomes not C or D, okay, etc. Okay, so what do you notice about these two equations? This equation and this equation over here. If I were to implement these in circuits, do they have the same efficiency, or is one of them more efficient than another? So let's count how many inputs. Let's count the sizes of the gates that we need right. So you guys are observing that the one on the left is more efficient, and that's correct. So in this case, I need a two input AND gate, and a 2 input AND gate, and a 2 input AND gate. That's 6 inputs in total. And then I need a 3 input OR gate. That's 9 inputs. And then I need 2 inverters. So that's 11 inputs in total. So I have 11 gate inputs in total. For here, I need a 2 input OR gate and a 3 input OR gate and a 2 input OR gate. So that's 2 plus 3 plus 2, that's 7. And then I need a 3 input AND gate. So that's 10. And then I need 3 inverters, an inverter for C and one for B and one for A. Okay, so that's 13 gate inputs in total. So the equation on the left needs less hardware to implement than the equation on the right. And this is only in this case. So in this case, sum of products is more efficient. But in other cases, it might be the case that product of sums is the more efficient way to implement the circuit. Okay, any questions? Okay, so if there are no questions, I'll move on to the final topic for today, which is universal gates. So a universal gate is a type of logic gate that can be used to construct all logic functions. So far we've been using AND gates, OR gates, and NOT gates, and our circuits have been comprising of these three types of gates. But it turns out that there are certain logic gates where my circuit only needs to have that one type of logic gate to be able to implement any logic function. The AND gate, the OR gate, and the NOT gate are not universal gates because I can't implement a circuit with just AND gates or with just OR gates or with just NOT gates. But two common universal gates that are used are NAND, a NAND gate, so this is an inverted AND gate, and a NOR gate. This is an inverted OR gate. Okay, I'll take a look at NAND gates first. So a NAND gate is a logic gate that implements an AND operation followed by a NOT operation. So it looks something like this. We have an AND gate and we put a bubble at the output. And the operation being performed here is C equals NOT A and B. Now there's one important thing to note here, which is that it turns out that implementing a NAND gate is cheaper than implementing an AND gate and a NOT gate separately. Okay, so logically, this NAND gate is equivalent to an AND gate followed by a NOT gate. However, in hardware, it's actually cheaper to implement a NAND gate as opposed to implementing an AND gate and then a NOT gate. Okay, in fact, it's cheaper to implement a NAND gate instead of just an AND gate. Okay, and this is an important observation. So NAND gates are cheaper to implement, and they are also universal, which means that if I have just NAND gates in my circuit, I can implement anything with just a NAND gate. Okay, and if we apply De Morgan's law to NAND, we get something like this. So if we apply De Morgan's law here, not A and B is equivalent to not A or not B. So this gate here at the bottom, we have an OR gate and we have the inputs to the OR gate inverted. This is also a NAND gate. So there's two different ways to draw a NAND gate. One of them is an AND gate with an inverted input. Another one is an OR gate, sorry, a NAND gate with an inverted output. Another one is an OR gate with an inverted input. Okay. Now let's see why. Yes.
And the second one doesn't mean that we have a first NOT gate for A, NOT gate for B, and then the OR gate for both.
Right. So logically, it's like having a NOT gate and a NOT gate and then an OR gate.
But the first we have only one.
Right, but that is logically, okay? But physically, when you actually implement this in hardware, you have just one gate, right? You have one gate that does all of these operations. Okay?
Oh, okay.
Right? So like I said, a NAND gate is cheaper to implement than an AND and an OR separately. So in the same way, a NAND gate, so this OR with inverted inputs, this is also called a NAND gate. This OR with inverted inputs is cheaper to implement than implementing an OR gate and an inverter separately. Okay, and I'm not going to go into the reasons why. There's people, our friends at ECE, they have entire courses on these things. If you're interested, we can talk about it in office hours. But it's just good to know that these NAND gates, which can be drawn like this or like this, are cheaper than AND and OR separately, and they are universal.
Okay, thanks.
Okay, so let's see why these gates are universal. Okay, let's see why these gates are universal. So first of all, if I have a NOT gate, I can obviously implement a NAND gate using a NOT gate. I just give that NAND gate one input. Okay, so a NAND gate with one input becomes a NOT gate, right? If I have here, I'm showing it to you as if I do A and A inverted, right? A and A is just A, and then you invert it. So here B is going to be not A. Okay. If I have an AND gate and I want to implement an AND gate using NAND gates, well, simply I can have a NAND gate and then I can invert the output. I've already seen how I can use a NAND gate to implement an inverter. So I can have a NAND gate followed by an inverter to get a an AND gate. Okay. If I want to implement an OR gate using an AND gate, I can have a NAND gate. And remember, this NAND gate is also equivalent to an OR gate with inverted inputs. So I just invert the inputs to the NAND gate, and I get an OR gate. Okay. When we were in class, it was much easier to explain why these two are equivalent on the board, because you can kind of erase things and redraw things, so it's much easier to explain. But if you try and if you replace this NAND gate over here with an OR gate that has inverted inputs, you can see that if you put an inverter here and inverter here, they cancel out the inverters over here, so you're left with so this over here becomes equivalent to an OR gate. And then finally, and most importantly, product of sums. So here, product of sums, right? A product of sums can be implemented using just NAND gates. And let me show you why. So here, if I invert the output at this NAND gate, and if I invert the output at this AND gate, and then if I invert the input at this OR gate, and I also invert the input at this OR gate, have I changed anything in the circuit? I haven't changed anything, right? I take the signal, I invert it, and then I invert it again. Same thing here. I take the signal, I invert it, and then I invert it again. Okay? Is that clear to everyone? Well, what are these two gates on the right? What are these two gates? This is a NAND gate, right? And this is a NAND gate. And what is this gate on the, sorry, these two gates on the left are NAND gates. And what is this gate on the right? This gate is also an AND gate, right? Because if you applied De Morgan's law, right, we saw that an AND with inverted input is equivalent to an OR, sorry, an AND with inverted output is equivalent to an OR with inverted input. So when we do a sum of products, rather than having a bunch of AND gates feeding into an OR gate, we can have a bunch of NAND gates feeding into a NAND gate, and that gives us a product of sum, a sum of products. Okay, and we said that we can implement all logic operations using a sum of products, and therefore it follows that we can implement all logic operations using just NAND gates. Okay, is that clear to everyone? Okay, great. Then finally, we have NOR gates. So NOR gates are similar to NAND gates, but they are an OR operation followed by NOT operation. So it looks something like this. You have an OR gate followed by a NOT operation. So that's equivalent to C equals NOT A or B. And just like NAND gates, implementing a NOR gate is cheaper than implementing an OR gate followed by a NOT gate. Okay, and if we apply De Morgan's law to a NOR gate, C equals A or B inverted is equivalent to C equals not A and not B. So a NOR gate can also be drawn like this. It can be drawn as an OR gate with an inverted output, or it can be drawn as a NAND gate with inverted inputs. Okay, and similarly, just like with NAND gates, we can implement an inverter using an NOR gate and pass the input as the only argument, so pass A as the only input. We can implement A or B by having A NOR B and then inverting the output. We've seen how to implement an inverter with a NOR gate. We can implement A and B by having A NOR B. Remember that this over here is equivalent to an AND gate with inverted inputs, and we have inverters to invert the inputs again. And then finally, the product of sums. So here, a product of sums looks like this. You have an AND gate, and you have a bunch of OR gates that feed into an AND gate, And just like before, if we invert the outputs of the OR gates, they become NOR gates. And if we invert the inputs of this AND gate, it also becomes a NOR gate. So having OR gates feeding into an AND gate is just like having NOR gates feeding into a NOR gate. So NAND gates can be used to implement sum of products easily, and NOR gates can be used to implement product of sums easily. Okay? Anyone have any questions? If not, then that is all for today. You can review this material in sections B.2 and B.3. And that's all for today. I'll see you next time.